Okay, let me start. Hello, everyone. My name is Ajay Jacob. I am the Director for Projects at the California Dreams Hub. It's my pleasure to invite Dr. Keisuke Shinohara. He received his PhD in solid-state physics from Osaka University in Japan. He is currently the principal scientist at the Teledyne Scientific Company. He leads the R&D on gallium nitride-based devices for RF and power electronics applications. He has more than 150 technical papers and given more than 50 invited talks, and he has written 3 book chapters as well. He's currently the chair of the IEEE MDTS Technical Committee on Microwave and Millimeter Wave Solid-State Devices. Today, Dr. Shinohara is giving us a talk on Teledyne's gallium nitride on silicon device library for the advanced RF and power conversion applications. Dr. Shinohara, the stage is yours.
Okay, thank you, Ajay, for your kind introduction. Hello, everyone, and Happy New Year. My name is Keisuke Shinohara. I'm with the Teledyne Scientific Company. Today, I'd like to present Teledyne's GaN-on-silicon carbide device technologies developed for advanced RF and power conversion applications. And all the technologies that I'm going to present today could not happen without invaluable contribution of my colleagues listed in here. And I would like to thank my many collaborators listed in here from universities, industries, and the government. And I acknowledge DARPA and ONR for their financial support on our R&D activities, as well as their technical guidance. I cannot change my slide. Sorry, I'm having issues of changing my slides to stage.
Peter, can you help? Can you go?
Stop sharing and then do it again, or?
Yeah, do it again and see.
Right, let me do that. Okay, so let me share screen. Okay, let me share. Do you see my screen?
No, not it.
How about this?
Yeah, it's coming. It's coming. Yes, I see your screen now.
And let me open my file again. Do you see?
Yes, I see your file. Can you scroll down? Scroll to the next slide. Yes, I can see your files. Yes.
You see my full screen, right?
Yes, it is full screen.
Okay, perfect. All right. Okay, sorry for the inconvenience. Okay, so this is an outline of my talk. So I'll begin with Teledyne's microfabrication capabilities and our foundry offerings. And then I'll talk about the background of this work and discussing AlGaN GaN heterostructures and their applications. And in the first half of my presentation, I'll talk about GaN-on-silicon carbide RF devices that includes a 2-transistor technology and 1 diode technology, which we call charge-enhanced HEMT, multi-channel bridge HEMT, Nano-Schottky diode. And the second half, I'll talk about the power switch devices based upon GaN-on-silicon carbide structure. And we present normally off p-GaN gate HEMT and a super heterojunction HEMT and Schottky diodes. And finally, I will summarize my talk with describing our future directions. So Teledyne Technologies is a publicly traded company with more than $5 billion in annual revenue. Our business units serve markets that require high-performance microelectronics and microsystems. Teledyne Technology has microfabrication facilities that span from R&D to high-volume production. Teledyne DALSA is one of the largest pure-play MEMS foundry in the world. Teledyne Imaging Sensors and Teledyne FLIR support captive foundries that develop high-performance infrared sensors. Teledyne Scientific is located in Thousand Oaks, California, and our fab supports R&D and early-stage prototyping and low-volume production of compound semiconductor and MEMS technologies. We are a member of the California Dream ME Commons Hub, where we are collaborating with University Nano Hubs and other DIB partners to accelerate lab to fab transitions. Teledyne Scientific Company was formerly Rockwell Science Center, and we have a long history of advanced semiconductor and MEMS development. Our microfabrication activities cover 3 areas. We perform sponsored contract research and development of high-risk microelectronics technologies for government agencies such as DARPA and ONR. Our areas of expertise are in compound semiconductors, heterogeneous integration, and MEMS technologies. We will mature technologies that are developed with R&D funding and develop foundry processes that can be offered to internal and external customers for prototyping and IC product development. Teledyne is an open foundry, and we are offering access to our foundry processes through Moses 2.0. Teledyne also offers cleanroom fabrication services to external customers for prototyping and low-volume production. In this engagement, we often work with customers who have performed initial tech development in University Nano Hubs and want to transfer processes to a more stable manufacturing environment as they scale up and mature the technology. We have a range of foundry IC technologies at varying level of process maturity. Our indium phosphide HBT technologies are learned most frequently and have the most mature design kits and IC models. That technology finds use in high-frequency millimeter wave and sub-terahertz power amplifier and transmit and receive ICs. Our indium phosphide HEMT technologies find use in millimeter wave low noise amplifiers and in wide bandwidth RF switches. Our gallium nitride HEMT technology, which I'm talking about today, find a use in high power, high efficiency, high linearity amplifiers, robust LNAs, and low loss RF switches. Our silicon RF interposer technology was originally developed under the DARPA SMART program and is tailored for the development of tileable millimeter wave phased arrays. And more details regarding our foundry offerings can be found by reaching out to Moses 2.0 or Teledyne directly. So now I talk about the background of this work. Like all of you, I have great advisors who invented HEMT in 1980. The right picture shows my professor Hiyamizu and Dr. Mimura are testing the first HEMT ICs, which I think is the DCFL logic ICs consisting of E mode and D mode gallium arsenide-based HEMTs. On the left top, I showed the hand drawing sketch of the energy band diagram of the HEMT drawn by Dr. Mimura. And in this structure, the two-dimensional electron gas is formed at the AlGas and gallium arsenide interface. The two-dimensional electron gas is spatially separated from the silicon dopant, which enables high electron mobility. The high electron mobility and low noise characteristics had a significant impact in improving the system performance of the satellite communication and the radio telescope back then. And HEMTs continue to find new applications because of the increased demand for the high frequency and highly efficient RF and the power electronics applications. So let's see the two-dimensional electron gas formed in aluminum gallium nitride heterostructures. Here I showed the standard AlGaN GaNAmP epitaxial structures grown on silicon carbide substrate. And as you can see in the band diagram, the 2-DEG is formed at the aluminum nitride gallium nitride interface. It is noted that the thickness of this 2-DEG is as small as 1 to 2 nanometer. And in this material system, without donor doping, the high density of electrons of 1e13s and high electron mobility in between 1500 to 2000 can be obtained. The high velocity at high field and high density of states due to the high electron effective mass and high breakdown field of gallium nitride make this material system suitable for transistor scaling, for high frequency and high power MMIC application, as well as high-speed, low-loss power converter applications. Okay, so such applications include base stations for 5G, 6G, and point-to-point backhaul, satellite communication, radars, and wireless power beaming for RF side. And in the power electronics side, the application include point-of-load power converters, envelope tracking power supply modulator, electric vehicle, aircrafts, ships, and large electronics in space. So here I show the basic block diagram of the RF front end with envelope tracking and the wireless power transfer systems. And each system consists of circuit elements such as RF switch, LNA, mixers, PAs, and DC-DC converters, and RF-DC rectifiers, together with the other passive components. So these circuit components require transistors and diodes, but their required performance for the transistors and diodes are very different. For example, for power amplifiers, for high-frequency application, it requires high FT and Fmax and high dynamic knee current density and high breakdown voltage and to achieve the high power density, as well as power added efficiency, large signal gain, and linearity are important. And for LNA, we need a good noise figure and associated gain, as well as linearity. As for the RF switch, we need a small R on, C off product, and the breakdown voltage and the high knee current density for the high power handling capability. And for DC-DC converter, we prefer to have normally off operations and a small R on QG for a given breakdown voltage, and a high breakdown voltage and high R on. So basically, depending on the circuits, the required performance or required specifications of the transistors and the diodes are very different. So in order to optimize those performances, our approach is to perform epitaxial and device co-design for specific functionality and optimum performance. So I'll talk about GaN-on-silicon carbide RF devices first. So this slide shows gallium nitride HEMT scaling to achieve high frequency operation of the transistors. Following the HEMT scaling law, one has to scale the transistor dimensions vertically as well as laterally by a factor of 2, to increase the frequency performance by a factor of 2, while reducing the parasitic resistance and the parasitic components in the same way. However, there are challenges. In order to reduce the vertical dimensions of a transistor, we have to reduce the barrier thickness, which may result in the reduced 2-deck density and increased current collapse due to an increased capacitive coupling between the surface states and the 2-deck. And using the short gate for the lateral scaling often limit the maximum voltage swing. And sometimes a nanofield plate is very effective to alleviate the electric field, which, however, increase the parasitic capacitance. So achieving the high gain at high frequency, such as W band, and high current operation and high voltage is very difficult because they are in a trade-off relationship. And I mean here by high current, not just the DC current density, but the dynamic current density. And similarly, I mean high voltage, not by the breakdown voltage, but by the maximum voltage, operational voltage with minimal current collapse. So here it shows the technology cross-section of Teledyne's charge-enhanced HEMTs designed for millimeter wave power amplifiers. We introduced silicon doping in aluminum gallium nitride, which is different from our conventional AlGaN GaN HEMTs where the silicon doping is not necessary. The reason for the silicon doping is there are two purposes for doing this. One is to increase the 2-deck density in access region to achieve the higher current density. And also, this silicon doping serves as a passivation of the states which exist at the GaN-on-AlGaN interface. And we have the curved gate foot corner, as you can see below in the TM images. And this structure alleviates the electric field peaking, a peaked electric field at the drain end of the gate without use of the nanofield plate. And then we use the surface passivation using LPCVD silicon nitride to minimize the surface trapping effect. And on the right, I shows the DC characteristics of such a transistor. This is output characteristics of a 90 nanometer gate devices with a source on drain spacing of 500 nanometer. And the device shows the very high new current density of 1.9 amps per millimeter with a very low R on of 0.43 on millimeter with the offstate breakdown voltage of over 35 volt. And on the right, the transfer characteristics shows the peak GM of 1.2 Siemens per millimeter, which is about 3 times larger than the conventional AlGaN GaN HEMTs. And for the high efficiency operation, we often bias the transistor at the deep class AB. So this transistor have the increasing GM when we increase the signal intensity, which will help to improve the high gain linearity that I'm going to show in the following slides. So this is the small signal RF performance of the charge-enhanced HEMTs. So on the left, I plot FTF max as a function of the gate length. And with a relatively long gate length of 90 nanometer, we achieve the FT of 160 gigahertz and Fmax of 320 gigahertz. And on the right, I shows the Fmax as a function of drain current density. And the green arrow represent the Fmax value along the resistive load line. So this device keep to have a high Fmax along the resistive load line, and which improves the large signal gain. And this is another important feature that we have accomplished in this structure, which is a suppressed trapping effect, which is a result of the silicon doping and surface passivation, as well as the rounded gate foot shape. So on the left, I plotted the knee current density as a function of quiescent drain bias. And as comparing to the conventional AlGaN HEMT, the CE-HEMT not only shows the higher knee current density, but also the knee current reduction at the high drain quiescent bias is much decreased. The conventional device shows 33% current collapse at the quiescent voltage of 20 volt, but the CE-HEMT shows the only 10% current collapse. And this phenomenon was confirmed in the drain current transient measurement, which is shown on the right. The blue line shows the drain current transient measured for the CE-HEMT, and the result is very consistent with the Prost IB measurement result. Okay, next, I show the load pull characteristic result measured at Ka band at 30 gigahertz. On the left, I show the P in P out characteristics of such a device, and the device shows the power density, output power density of 4 watt per millimeter at the drain quiescent bias of only 10 volt, with an associated PAE of 54%. And as you can see, the gain curve is so linear, and it doesn't show the typical soft gain compression observed in traditional GaN HEMT. And as a result, the peak PAE was obtained at P1 dB conditions. So this technology is very suitable for the linear power amplifier applications. And on the right, the obtained output power density is plotted as a function of quiescent drain bias. And the slope of this linear line represent the effective dynamic knee current density. So our data shows the knee current density of about 1.9 amps per millimeter, which is consistent with the DC knee current density all the way up to 15 volt, which means that the device is not experiencing a severe current collapse up to such a high voltage and high power density. Based upon this technology, we have developed the MMICs, and here I show the one example, which is a broadband 3 to 13 gigahertz high power NDPA MMICs, which was developed under ONL EWT program in collaboration with Qorvo. The circuit demonstrated a peak P out of 38.4 watt with a peak PAE of 22.7 to 34.7%. with a gain of 15 to 17 dB. Under ME Commons CA DREAMS NG GaNAmP project, we are collaborating with Teledyne and Northrop Grumman, and the purpose of this project is we develop and provide a device chiplet, which is designed in Teledyne's GaN CE-HEMT process to support rapid prototyping and heterogeneous integration in the Teledyne silicon interposer IC process. On the left, you can see our CE-HEMT chiplets for two differential designs that have 4 by 40 micron gate fingers, as well as 8 by 100 micron gate fingers. And in the middle, I forgot to mention one thing. We use the dry etch chip singulation process to fabricate these chiplets. And this process enables to obtain a very small edge roughness of as small as 1 micron, and device to chip edge misalignment is less than 3 micron. And these chiplets were integrated through the RISC silicon interposer, which is shown in the middle. And they designed the X-band RF switch circuit using our devices. And the right is showing the small signal data and comparing the measurement and the model. And they show a very good agreement between them. And the result shows the very low insertion loss of less than 1 dB. And the right bottom, it shows the power handling test. And it didn't show any compression up to the power level of 2 watt. So we also performed power handling capability of our RF switch devices based upon CE-HEMT, which is shown in the next slide. So this is a collaboration work with Professor Nick Miller at MSU and Dr. Toshifumi Nakatani and Dr. Isabel Terris at Maxcentric. And we designed the device cell, RF switch power cell, to characterize the power handling. And as you know, the power handling capability is determined by the on state of the switch as well as off state. And the power handling limited by the on state is determined by the maximum current density of the transistor. And off-state power handling is determined by the breakdown of the devices. Since the CE-HEMT transistor, CE-HEMT technology enables a very high near current density, close to 2 amps per millimeter, and have a reasonable high breakdown voltage of over 35 volt. We could achieve more than 10 watt of power handling at 10 gigahertz for the device cell size of 7 by 100 micron. Okay, so next I'll talk about a more exotic device design, which we called multi-channel buried dual gate bridge HEMT, designed for linear PA and RF switch applications. So as you can see in this illustration, the bridge HEMT consists of multiple two-leg channels stacked on top of each other. The idea of using multiple channels is to increase the current density and to decrease on resistance. So, but we cannot use the top contact gate because the top contact gate only modulate the top channel or probably second channel. But in order to modulate the multiple channels simultaneously, we bury the gate. And then the gate is contacting the side of the two leg. So the transistor behaves like the MESFET, utilizing high electron mobility two-dimensional channels. The transistor current is modulated by modulating the width of the channels using this lateral gating. So in the middle, I show the cross-sectional TEM image of the fabricated devices. This device have 24 channels. Each channel consists of silicon modulation doped AlGaN and aluminum nitride interlayer and the gallium nitride channel layer. And we stack these structures on top of each other. And we can control the two-leg density in each channel by the silicon doping concentration, as well as the number of total channels. So on the right, I plotted the electron mobility as a function of net two-leg density. Like I said, the net to the density can be controlled by the number of channels and the doping concentration. And we could obtain a very high charge density up to 1.3 times 10 to the 14th, which is more than 10 times as large as the single channel gallium nitride HEMT, while maintaining a reasonably high electron mobility of 1500. And this technology allows us to choose the 2-dig density in each channel, like I mentioned in the previous slide. Why it is important? It is important because it is known that the electron velocity at the high electric field is depending on the 2-dig density. And this is theoretically predicted by Professor Professor Jenner at the University of Notre Dame. He's now at Cornell. And with increasing the 2-dig density in the single channel, the photon emission rate increases, and that resulting the reduction in the electron velocity at high electric field. So by having the smaller 2-dig density in each channel, the saturated electron velocity can be increased. So in the multi-channel configuration, we can minimize the 2-dig density in each channel, but we can stack them up to have the high net 2-dig density. So here I show the electron velocity experimentally measured as a function of the 2-dig density. So in the multi-channel structure, we can achieve high electron velocity even for the high 2-dig density by reducing the 2-dig density per each channels, which is effectively improve the high frequency performance of the transistors. So here I shows the 6-channel Schottky gate bridge HEMT result. And on the left, it shows the IB characteristics. And as you can see, this transistor behave differently. Normally, the GM peak is obtained around 0.2 amps per millimeter in the conventional AlGaN GaN HEMT structure, while in the bridge HEMT, because the transistor operates like a MESFET, the GM keep increasing with increasing the drain current. And on the right, I shows the power performance measured at 30 gigahertz. And the transistor demonstrated output power density of 7.1 amps, 7.1 watt per millimeter with associated PAE of 39%. The obtained PAE of these devices are limited by the gain, so this device still need improvement for improving the frequency performance. And we also developed the model to explain this device operation like MESFET. And I show here the equations and showing how the channel modulation is done by the lateral gating. And a very simple MESFET model can explain these IB characteristics of the bridge HEMT. This is the 24-channel MIS-gate transistors. So the number of channels increase the drain current density. Now, the maximum current density goes up to 4 amps per millimeter. And if the current density is normalized by the actual channel width, it reaches 7.3 amps per millimeter. And on the right, I shows the transfer characteristics. And this device has the linearity enhancement features built in. As you can see, the channel width is slightly tapered. So the stack channel have a slightly different channel width, which means that the threshold voltage, each channel is slightly shifted. So the transfer characteristics of such a transistor is a superposition of different transfer curves. On the right bottom, I showed the mathematically calculated GM curves with multiple channel widths, which is shown in the red curve, as compared to the single width case. So by using this superposition technique, we can reduce the GM second prime, which is important for the linearity enhancement at low power level. As a result, this transistor shows a very small second prime GM curves, as well as the flat GM at high current density. So here I show the RF switch performance benchmark, which of our technologies in comparison to the RF SOI technology, as well as Northrop Grumman's slick FET technology. The blue data points is from CE-HEMT, and the yellow square is for the bridge HEMT with 24 channels. And by using these technologies, we could reduce the ROC figure of merit better than the RF SOI, but it was not as good as the energy slick FET. So we recently come up with different device designs, which I didn't discuss this time, but we will present this result in the near future. But we could succeed in obtaining a very small ROC product of 50 femtosecond in the recent devices. Next, I'll talk about Nano-Schottky diode designed for millimeter wave rectifiers. So in this structure, we use the lateral metal contact to the 2-deck. This structure enables to minimize the junction capacitance because, like I said, the 2-deck is confined within 1 to 2 nanometer, so the contact area size can be minimized. While at the same time, the high electron mobility and high density of 2-deck minimizes the series resistance. And we used N plus GaN rigorous process to minimize the parasitic resistance associated with ohmic contact. So in the middle, I shows the CV characteristics of such a device and also the IV characteristics. And the device shows the very low turn-on voltage of 0.6 volt with very high current density exceeding 1 amps per millimeter. And we also optimize electric field distribution, enabling the breakdown voltage of over 62 volt. And the C-on, C-off ratio is 4.6, as shown here. And on the right, I plotted the cutoff frequency, which is 1 over 2 pi Rs Cg0 as a function of breakdown voltage in comparison to the conventional gallium arsenide Schottky diodes, as well as vertical gallium nitride Schottky diodes. So this device shows the 10x improvement. So we maintain the similar or even higher cutoff frequency while improving the breakdown voltage by a factor of 5 to 10. And we use this device to demonstrate the rectifier circuit. And here I show the summary of the circuit. On the left, the obtained result of RF to DC conversion efficiency is plotted as a function of incident power density in the blue solid lines in comparison to the previous result. And with our result, with our technology, we could obtain more than 50% conversion efficiency at 94 gigahertz with high power density. Okay, so now I'll talk about power devices based upon GaN on silicon carbide technology. Under DARPA space program, we have developed GaN super heterojunction HEMT for radiation tolerant for converter applications. Here it shows the operation principle of the super heterojunction HEMT as comparing to the conventional source field plate HEMT. And on the left, it shows how the two-dimensional electron gas depletes with increasing drain voltage at off state. In the source field plate devices, the 2-deg is laterally depleting with increasing the drain voltage. And when the pinch-off voltage of the source field plate kicks in, the 2-deg under the field plate is depleted. And then 2-deg keep depleting laterally with increasing drain voltage, which result in the peaky electric field as shown on the left bottom. And the electric field laterally expands while the peak electric field at the corner of the gate and the source field plate peaks at that locations. While in the super heterojunction, that consists of the p-type gallium nitride material deposited on the aluminum gallium nitride HEMT structure. And this device is basically consists of the conventional AlGaN HEMT and a vertical PN diode. And we designed the magnesium concentration, doping concentration in the p-GaN HEMT to match to that of 2-deg, which we call the charge balance. In such a device, when you increase the drain voltage at off state, when the PN diode reaches to the pinch-off voltage, the entire 2-deg under the p-type layer is depleted. And the drain voltage at the drain of the gate is pinned at this pinch-off voltage of the PN diode, and all the electric and all the voltage after that is applied in between a gate and drain. So as a result, we can maintain the uniform electric field and minimize the electric field peaking as seen in the source field plate devices. This uniform electric field allows us to minimize the gate-to-drain spacing for a given breakdown voltage. As a result, we can minimize our own QG for a given breakdown voltage. And this figure merit is very important to achieve the fast and efficient power converters. And also the uniform electric field allows to achieve the low dynamic RON, and it minimizes the gate-to-drain capacitance, which is important for fast switching. And in addition, the uniform electric field increases radiation hardness because it is known that a single event defect is caused by the high electric field point. And this device doesn't have the field plate dielectric as compared to the source field plate, and the absence of such a dielectric minimizes the SEDR, single event dielectric rupture, which also help to improve the radiation tolerance. So this is a device simulation result comparing the source field plate device and super heterojunction, which is performed by Professor Longmin Chu at Penn State University. As illustrated in the previous slide, the super heterojunction shows the uniform electric field, while the super heterojunction shows the laterally expanding field distribution with increasing the drain voltage. And on the right, it shows the gate-to-drain capacitance as a function of drain voltage. And as you can see, the gate-to-drain capacitance for the charge balance super heterojunction, which is shown in the blue lines, is much smaller than that of the source field plate devices. And it drastically reduces gate-to-drain, the gate charge in between gate-to-drain regions. So in order to make the normally off super heterojunction devices, we first demonstrated the normally off p-GaN gate devices using our conventional AlGaN HEMT structures. And here I show the device cross sections having the P plus GaN gate, which was regrown by MBE. So the sheet resistance of AlGaN GaNAmP is 300 ohm per square. And this device shows the threshold voltage of 0.8 volt. And a low R-on of 1.42 and QG of 12.23, resulting R-on QG of 17.37 milliohm nanocoulomb. The breakdown voltage of this device is more than 200 volt. As you can see in the transfer characteristics in the middle, the device shows a negligible hysteresis, showing the good quality of this p-GaN gate device structure. Here it shows how we extract the gate charge of such devices. And on the top, I shows how the transistor 2-deg is accumulated when the transistor is switched from off state to on state. And we use the CV integration method to extract the gate charge in here. And we measure the CGS plus CGD as a function of CDS at on state. And we measure CGD at off state as a function of drain voltage. And by integrating those CV characteristics, we obtained a QG. So here I shows the super heterojunction result, and it shows a very good pinch-off operation with the normally off condition. The R-on of this device is 2.76 ohm millimeter, and the threshold voltage is again 0.8 volt. And the breakdown voltage of this device was 80 volt, which is limited by the drain leakage current, even though the drain leakage current is very low. So we are working on this to further reduce the gate to drain to source leakage current in order to improve the overall breakdown voltage. However, this device shows a very small gate charge because of this PN junction, and around QG of 21.5 milliohm nanocoulomb was obtained. So here I shows the specific feature obtained in the super heterojunction as compared to the source-connected field plate. On the left, I show the off-state gate drain capacitance as a function of drain voltage at off-state, and at the PN diode pinch-off voltage of 8 volt, the 2-deg is fully depleted, which resulted in a very low gate-to-drain capacitance. And that is a reason for the reduced gate charge of this device. And in terms of the dynamic R-on, the super heterojunction maintained the raw dynamic R-on all the way to 50 volt. This is a result of the uniform electric field obtained in this device. The Schottky diode built in the same super heterojunction HEMT epitaxial structure is also very important because we will need the diode structure, especially in the low side switch in the DC-DC converter applications. Here I shows the obtained IV characteristics in the linear and the log scale. And device shows the turn-on voltage of 0.5 volt, and the breakdown voltage of over 100 volt was obtained. So here I show the power switch figure merit benchmarking, which is R-on QG, plotted as a function of broken voltage. And our p-GaN gate HEMT shows the about 3 to 5 times better performance as compared to the best GaN-on-silicon power switch devices reported previously. And we also showed the good performance of the super heterojunction devices, while there is still a big room to improve the breakdown voltage in the super heterojunction devices. Okay, so let me summarize my talk. We have successfully demonstrated enhanced performance of RF and power switch devices through epitaxial and device co-design approach using 2-deg in AlGaN heterostructures. We will continue to advance device performance while simultaneously maturing device technologies and increasing MRL and TRL levels of each technology. We are also working on 2.5D and 3D hybrid integration process of multiple GaN-on-silicon carbide technology optimized for to obtain higher circuit performance. We offer GaN-on-silicon carbide discrete device products and MPW foundry services through Moses 2.0. And if you have any questions and inquiries after this presentation, please send an email directly to me. Okay, thank you so much, and I'll take any questions.
Thank you, Dr. Shinohara. It's a great presentation, lots of results, lots of device schemes that you have shown, a variety of plethora of devices and very interesting devices. Okay, let's open up any questions here. You can either take the mic and ask, or you can type your questions here and I will ask to Dr. Shinohara.
Yeah, I cannot see the questions. Oh, okay.
Yeah, there is the first question came in. What is the impact of vertical scaling on speed? I probably missed the study in your presentation. That was the first question from Barry Wu.
Okay. Yeah, so vertically scaling very important for achieving the high frequency performance in a transistor with the shorter gate lengths, because you want to maintain the aspect ratio of the shorter gate lengths and the vertical sizes. So essentially, you will need to reduce the vertical scaling in order to increase the transistor speed. Does it make sense?
Yes. The next question from Barry is, what is the mechanism of silicon doping in AlGaN, mitigating the current collapse? I mean, I had the same question here. Yeah. How do you do the silicon doping here? And how precise is, and what's the doping density?
Yeah, I think, silicon doping is done similarly to the way that is done in a conventional gas HEMT. So we just introduced the silicon doping in the aluminum gallium nitride layer, okay? And it helps to, in terms of current collapse, right? So it is known that there is the traps in at the interface of GaN on aluminum gallium nitride. And by introducing silicon doping, we think that it passivates some of the interface traps, and that result in a reduced current collapse.
And what is the doping density?
It's about ranging from 5e19 range.
Okay. And what is the thickness?
It's about 10 nanometer.
10 nanometer, okay. The third question from Barry is, in bridge HEMT, what is the optimal spacing between the gate wells? And is it wide distribution of fifth is a concern, if the wide distribution a concern?
Yeah, so that's a very good question. We optimize the spacing between the channels in order to control the effective 3D density of the channel. Because if you make too close, it becomes very hard to pinch off using the lateral gate. So essentially, you have to control the doping density and the distance of the to the channels in order to control the effective 3D density, to optimize the channel modulation efficiency by the lateral gating.
One follow-up question here with respect to the bridge is, what is the source and drain width?
Source and drain width. Source and drain. Yeah. Source and drain distance, you mean?
No, not the distance is the same channel length, but the width of how big are these source and drain? Or is,
channels, you mean?
Pardon?
These are multiple channels, you mean?
Correct. Yeah, yes.
Yeah. Okay, it's about 100 nanometer. So if I show you the picture again, oh,
Oh, sorry, you have to, yeah, you have to move from that as well. Sorry. Peter, can you move this away?
uh, it's okay.
I
Okay,
took
it's
it away. I'm sorry.
yeah, it's about 100 nanometer channel width.
Okay.
Yeah.
The next question is from Emily. What was the MRL of the 90 nanometer CE-HEMT that demonstrated the 120 gigahertz cutoff frequency?
Yes.
Or what was the achieved cutoff frequency for the RF switch made with CE-HEMT?
Okay. So the current MRL TRL of our 90 nanometer CE-HEMT is MRL TRF 5.
Oh, okay.
Yeah. And then cutoff frequency for the RF switch made with a CE-HEMT. Yeah. So it is the same device. So it's a 120 gigahertz.
Mm. Which of these devices that you showed is an MPW at MOSFET 2.0?
Yeah. So among these gallium nitride technologies that I showed today, the
Yeah.
CE-HEMT is the most mature technology. So the MPW run we provide for the CE-HEMT. And also, we also provide Nano-Schottky diode process as a MPW run.
So you showed that the last device was the super junction nanodiode. Is that the one that is okay?
No, sorry. That
No,
one is,
no.
yeah, that's a power switch and a power Schottky diode. Those are still very early stage. It's a still developmental stage. So we have RF, CE-HEMT, and Nano-Schottky diode, which I demonstrated for the rectifier applications.
Hmm. I also, so is there any other questions? I mean, I see that any other questions? Oh, there is an anonymous attendee who is asking a question about the trap density. Is there any data on trap time constant?
Unfortunately, we don't have those data yet.
Okay. I have a question, Kiske, and that is about super heterojunction
Okay.
devices. Again, it is regarding the doping density and also the super heterojunction itself. What are the thicknesses or dimensions that we are discussing here? And you also have very complex structure here where the source is, I mean, you have the thickness variations between two gallium nitride and the P plus gallium nitride.
Yes. So this P minus gallium nitride is actually grown as an initial growth. Okay.
Mm.
And
Mm.
then in terms of the thickness, right? So let's say we dope magnesium of 1E18, okay, and 100 nanometer, which basically have the magnesium concentration 2D wise is 1E13, which matches with the 2DEC. Okay, and then the magnesium is activated by the field, electric field. So when you apply electric field, those holes are activated from the doped magnesium. So, and then at some point, when the 2DEG is fully depleted, the hole in the P minus GaN is depleted simultaneously. So that's the charge balance condition. And while in the P plus GaN, those are regrown GaN. So we have to etch off the P minus GaN, stop on aluminum gallium nitride, and then we regrow P plus GaN using MBE to enable the normally off operation.
Okay. Okay. Thank you so much, Kaisuke. And the next week's seminar. Can you go to the next slide, Peter? And the next week, it will be Professor Prelsic from UC San Diego. Nuria Gonzalez Prelsic would be giving us next week's seminar. And once again, thank you, Dr. Shinohara.
Thank you.
And thank you all.